Welcome back. We're going to do one more example of isomers. And for this one, we're just going to go directly to the formula C6H5Cl. And looking at the index of hydrogen deficiency for this molecule, we do have 6 carbons, so we input 6 for the value of N. 2 times 6 is 12, plus 2 will be 14. The formula contains 5 hydrogens, but we also have 1 chlorine, so there's a total equivalent of 6 hydrogens in the formula. So we'll change that to 6. And subtracting 6 from 14 gives us 8. 8 divided by 2 is equal to 4. All right, so what this is telling us is that there's a number of possibilities that we can go with. In fact, there's a lot. We have 4 double bonds that could give us a value of 4 for the IHD. We could have 4 rings. We could have 3 double bonds plus 1 ring. We could have 2 double bonds or plus 2 rings, or we could have 1 double bond, 3 rings. And we could also start introducing triple bonds, right? Because a triple bond accounts for an IHD of 2. So you could have 1 triple bond and 2 double bonds, or 1 triple bond and 2 rings, or you could have 2 triple bonds, period, to end up with an IHD of 4. All right, so first things first, we'll look at the 4 double bonds. Now, for you to have 4 double bonds, you will have to have probably more than 6 carbons to make this work out. And even though chlorine is a non-hydrogen atom, it can only have 1 bond, so you cannot really make double bonds to it. At least not for the molecules we're going to be looking at in this class. So 4 double bonds doesn't seem possible for this structure. Same thing with rings. Having 4 rings with only 6 carbons is not the easiest thing, and I actually tried. I tried to see if you could make them, but you just can't do it and still end up with only 5 hydrogens in the structure. All right, now, but this is the interesting one. If we decrease the value of double bonds and substitute a double bond for a ring, then this is actually perfect, because 3 double bonds and a ring, well, that's your benzene ring. And that's what I told you in a previous video, that if you do end up with an IHD of 4, there's a good likelihood that you do have a benzene ring. So we're going to start by drawing that. Here's your benzene ring, hexagonal with 3 double bonds. So 1 ring, IHD of 1. 3 double bonds, total IHD of 3. Altogether, IHD of 4. And of course, you still have to have a chlorine, so we place the chlorine right there, and we're done. So this is chlorobenzene. And that's basically it. It doesn't really matter where you put the chlorine, it will still be chlorobenzene. All right, now, if you look at the other categories, because there is a chance that this will be a benzene ring, but you need some extra information to completely validate benzene being the molecule that you have present for your chemical formula. But there's other possibilities that you could also go through that will account for the same IHD. For instance, you could have 2 double bonds and 2 rings. And right here I'm showing you a few representative examples that make this happen. You have this cyclopropene bound to another cyclopropene structure with a chlorine sticking out of it. If you count the number of hydrogens, you have 1 hydrogen here, 1 hydrogen there, 1 hydrogen here, so that's 3 altogether, plus another one, 4, plus a 5th one, that's 5. And then this one right here doesn't have hydrogen, so we end up with 5 the same way. You could also have spiral compounds, that those actually work out as well. So here you have 1, 2, 3, 4, and 5 hydrogens altogether. And here's where it gets a little complicated, because if you start fusing further rings and further rings, not to say that these molecules cannot be made, but in terms of counting the rings, it's not as straightforward as it was with, cyclic ring bound to another cyclic ring with an actual bond. By the time you start getting to multiple spirals like this one right here, you could still make it work out, but this will be cases that probably you won't be dealing with. But just be aware that further fusing doesn't exactly follow the rules of the IHD formula. So if you look at this formula, you have 1 hydrogen right there, you have another one right here, no hydrogens, no hydrogens, 1 hydrogen, so that's 1, 2, and 3 so far. Over here you have another one, and right here you have another one. So you have 1, 2, 3, 4, 5, which works out for that structure over there. So just be aware of this type of thing. It may happen, you might see it from time to time. The sure way to know about the rings, if you start increasing rings, is to only have 1 spiral, or have rings connected to each other, not be as spirals at all. All right, the other possibility will be to have one triple bond and two double bonds. That will give you an IHD of 4. And since you have 6 carbons, uh, two possibilities that you can have, and they're not the only ones, but the ones that are perhaps the most interesting to look at are the one where you start with the alkyne. So this is 1, 2 carbons long, 3, 4, 5, 6. And now notice that for the last set, here's where the two double bonds appear, and they are bound to the same central carbon right here. So this is actually a linear molecule. This fragment right here is known as allene. And altogether you have 1, 2 double bonds and 1 triple bond. So now let's see if we end up with 5 hydrogens as the formula predicts. The terminal alkyne carbon here contains 1 hydrogen. This one doesn't have hydrogens. This one right here has 2, so this is up to 3 so far. This carbon doesn't have any hydrogens. That one doesn't have any hydrogens. This one has 2, so that's 5 altogether. And then the alternative will be to have just the alkyne followed by alkene followed by another alkene in sequence without connecting to the same carbons. And similarly, this has 1 hydrogen, this has none. This has 1 hydrogen, so we're up to 2. This one has 0, so we still have 2. This one has 1, so now we have 3. And this one right here has 2, so we have 5 altogether. And of course, the cis-trans variations and putting the chlorine on different carbons will give you all the different derivatives. But be sure that when you're coming up with derivatives that you don't break up the octet rule. If you violate the octet rule, it's game over. You don't have a correct structure at all. So make sure that your carbon has no more than 4 bonds. So the one thing you will not want to do is take this chlorine and place it on this carbon that contains an alkyne, because then you end up with more than 4 bonds. Okay, now 1 triple bond and 2 rings. One representative example will be this fused bicyclo ring that contains an alkyne coming out of it. And this is really the only one that I could come up with that contains 2 rings, because you don't have enough carbon content. To have the triple bond, you do have to have 2 carbons to make up the triple bond, so that only leaves you with 4 carbons left over. And this bicyclo gives you the correct number of hydrogens. So notice that here you have 1 hydrogen, 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 so that's 4 altogether. And of course, you have 1 hydrogen at the end right here, giving you 5. So not to say that these molecules are just as stable as benzene. Most of them are not. Benzene, in fact, is probably the more stable out of them, which is why when you have an IHD of 4 or slightly higher, there's a really good chance that you're dealing with benzene. But just be aware that you can come up with other structures, albeit not the most stable molecular structures, that can provide you with that high of an IHD value. And even though in this example we weren't able to have 4 double bonds or 4 rings, if you were to have more carbons present in your formula, that may actually be a possibility. Okay, now 2 triple bonds, this is perhaps the simpler case, because you could draw the triple bonds at the ends. So you have 1, 2, 3, 4, 5, 6. So notice that we're separating the 2 triple bonds with 2 carbons, and here I'm placing the carbon right in the middle. But we could also have a separation of only 1 carbon, in which case we only have 5 carbons in the main chain. So the 6th one is added, basically branching off of the main sequence. Here I'm placing it on the middle carbon. Over here I'm placing the 6th carbon at the end of the alkynes. And I'm also, placing that in there because here I'm giving you an example that doesn't contain a carbon separating the alkynes. The alkynes are actually directly bound to each other. So these are not the only possibilities, but these are some of the main ones that I wanted to show you. So alkynes can also help you increase that value of IHD. So it's something to keep in mind. All right, now with all of that, I think we are done with this lecture. So just to give a little synopsis of everything. Regarding the IHD formula, you want to use the alkane formula, 2n plus 2, and subtract the number of equivalent hydrogens from the 2n plus 2 formula, and then divide the whole thing by 2. And the equivalent hydrogens are determined as follows. If you do have hydrogens in your actual formula, you count them all. If you have halogens in your structure, you count them as if they were hydrogens. If you have oxygen or sulfur, you ignore them. And if you have nitrogen or phosphorus, you subtract as many hydrogens as you do have nitrogens and phosphorus from the overall formula. The n plus 1 peak is going to tell you how many carbons you have. Simply divide the percentage by 1.1 if and only if the n plus peak is up to 100%. The n+2 peak will allow you to determine the value of chlorine, the amount of chlorine, the amount of bromine, and the amount of sulfur. And remember these percentages: 33 and multiples of 33 for chlorine, 100 and multiples of 100 for bromine, and multiples of 4 for sulfur. That will be only in the n+2 peak. And this is if and only if the n plus peak is out of 100%. And lastly, if the molar mass is odd, you must have at least one nitrogen in your formula. If not, then you have to have odd numbers of nitrogen. If the molar mass is even, you must have an even number of nitrogens, with 0 counting as an even number. All right, that concludes the lecture. So in the next one, we will talk about infrared spectroscopy, and that will be complementing what we've talked about right now, which is basically finding out what the chemical formula of the compound is. With infrared spectroscopy and later on NMR spectroscopy, we're going to find out the exact molecular structure that we're dealing with out of all the possible isomers. Okay, so see you in the next lecture series. Bye bye.